Welcome to this lecture. In the last lecture, we discussed about the decision table based testing, where we considered various combinations of conditions. We will proceed from there. We will look at the cause effect graphing, and then we will look at the pairwise testing, Twoway testing and pairwise testing. But before that, let us do a small quiz based on the decision table based testing. So, the problem here is that we have a e-commerce site, and here a member gets 10% discount on purchases lower than 2000 rupees, and if it is more than 2000, they get a 15% discount. Purchase using some specific card like SBI card fetches additional 5% discount, and if the purchase amount after all discounts exceeds 2000, then shipping is free, otherwise the shipping is charged. Now, to develop the decision table based testing, we need to identify the conditions and the actions. The next step would be to consider all possible combinations of conditions and then identify the actions corresponding to those, and we represent that in the decision table, and each column in the decision table becomes a test case. Now, let us first identify the conditions. If we read here, member gets 10% discount for purchases lower than 10,000. So, a condition here is that if the purchase is lower than 2000, then you will get, if this is yes, then 10% discount, if it is no, then it is 15% discount. Whether payment is made using SBI card, this is another condition. So, let me also write down the condition C 1 and C 2, and this fetches an additional 5% discount. And the third condition is that the purchase amount after all discount exceeds 2000, this is the third condition. And the action part is the decision is 10%, 15%, additional 5%, and then the total amount exceeds 2000, then shipping is free. We can write C 1, C 2, C 3, C 4 in the top rows of the decision table, and A 1, A 2, A 3, A 4 are the actions, and then if C 1 is true, that is purchase is lower than 2000, C 1 is yes, C 2 is it is not purchased using SBI card, C 3 is the purchase amount exceeds after all discount 2000 rupees, we will say no, and then we will see that the discount is 10% yes and the rest are no, and so on. We need to design this table, but just one word of caution is that if this is no, if this is yes, purchase amount is less than 10%, then automatically the purchase amount of discount after discount will be less than 2000. So, we cannot have that this is yes and this is also yes. If this is yes, this has to be no. So, there is a dependency between these two, and that we have to take care while developing the decision table. As we were mentioning earlier, the cause effect graph provide a systematic technique and graphical symbol based on which we can explore the combinations of different inputs, represent them as nodes, edges in a graph, and then once the graph is developed, we can easily translate the graph into a decision table. In the graph, we can have constraints like and, or, etc., and also we can have intermediate nodes between the input and output, which will help us to simplify the graph. We explain this cause effect graphing using a simple example that we were discussing earlier, that if the deposit amount is less than 1000, then the rate of interest is 6%, 7%, 8% for deposit up to 1 year, over 1 year and less than 3 year it is 7%, 8%, the deposit is 3 years and above. But if the amount is more than 1 lakh, then the rate of interest is higher, 7%, 8% and 9%. Now, we want to develop the cause effect graph for this, and then once we develop the cause effect graph, we will translate that into a decision table, and then the decision table will give us the test cases. First, let us do the cause effect graph. The cause is the conditions on the input, and the action is the output. So, here the conditions on the input, if it is the amount of deposit is less than 1 year, 1 to 3 or 3 year, and also another condition is that whether it is less than 1 lakh or more than 1 lakh. So, we represent that here the causes, deposit is less than 1 year to 3 year, greater than 3 year, and also whether the deposit amount is less than 1 lakh or greater than equal to 1 lakh. And we also note down the different effects or the actions, which are whether the rate applicable is 6%, 7%, 8% and 9%. Now, each of these we represent in the form of a graph. We write the input conditions and the actions, and then specific combinations of the input conditions, they give rise to specific actions. For example, if it is less than 1 lakh and it is less than 1 year, we write a AND symbol here. We write a AND symbol here to show that this is the constraint that both these conditions must hold, and then the corresponding effect or the action is E 1. We have also a constraint in the form of or any of this. If it holds, then the action is E 2 and so on. Can easily translate the input into this graph form, cause effect graph, and once we have done the cause effect graph, this can easily be translated into a decision table. We just identify from the graph that if certain causes are both 1, then the effect is 1 and so on. And then once the decision table is developed from cause effect graph, we get the test cases. Now, let us discuss how to reduce the number of test cases, because in some situations where the input data are too many, input conditions are too many, the number of test cases increases exponentially, and that can become a very large number, billions or trillions of test cases, and it becomes impossible to test the software, even though we are able to design the test cases using a decision table based testing. The pairwise testing helps us to reduce the number of test cases. Let us see how do we go about developing the pairwise test cases. In the motivation for pairwise test cases, we just take the same example here that we were discussing earlier, that we consider the font in a word processing software, and the user has to choose the specific font to be used, the style to be used, and the size of the font, and also can use these check boxes to indicate whether it should be a strike through, double strike through, superscript, subscript, and so on. Now, based on this, how many test cases can be designed on a decision table based testing? Okay, we count here 4, 3, 7, 3, 10. So, there are 10 check boxes here, and each of these either it is checked or unchecked. And if we consider all possible combinations of these, then it becomes 2 to the power 10. So, only based on the check boxes it becomes 2 to the power 10 or 1024. But then what about the other options, that also we must consider. Let us assume that there are only 10 here, it may be more, but for our simplicity we just consider that there are only 10 font types to be selected and 10 styles to be selected and 10 font size to be selected, and then how many test cases? We need to multiply 2 to the power 10 with 10 to the power 3, and this becomes 1024,000. Too many test cases for anybody to test the software. It will take years or tens of years, but how do we go about testing this kind of software, because these are very common, and I was saying that even controller software also have similar characteristic, that many input variable combinations arise and different actions corresponding to those. And let us see how to reduce the number of test cases such that it becomes possible to test this easily, and also at the same time we do not want to lose the thoroughness of testing. We need a technique which will reduce this 1024,000 into, let us say, just 8 or 10 test cases, and also the thoroughness of testing should not suffer too much. Of course, it cannot be exactly as thorough as testing with all possible combinations of conditions, but it should be 99% or so thoroughness must be achieved, and that is achieved by the pairwise testing. Let us see the ideas behind this. So, here the problem that we are addressing is that the system has only one state and there are many inputs, and we need to consider the combinations of these input. But you may say that what if the system is state based and there are multiple states of the system and transitions among state, then the problem is more complicated. We need to design the combinatorial tests for every state of the system and also every transition, and therefore, the problem becomes more complex. But we are now restricting to a simpler problem where the system has only one state and these are the inputs, and we need to test using various possible combinations of the inputs. The key observation here is that often the bugs are caused by interaction among few factors. Even though we have hundreds of input, but then some specific 2 combination among these might cause the bug, or maybe 3 combination, or in general T combinations may cause the bug. And if we consider all possible t combinations among the input, then we can dramatically reduce the number of test cases, and still we will have a effective bug detection even very reduced number of test cases. Let us discuss this idea further. Let us assume that a program or a function takes these as the input. Let us say it takes input the interest rate, the amount borrowed, the number of months for which the amount is borrowed, and the down payment, and then the payment frequency. And based on that, it will, let us say, give us how much to be paid every month. That is the function. If we look at the parameters here, there are 1, 2, 3, 4, 5 parameters, and there are many possible equivalence classes, boundary values, and so on for each of these. If we consider all possible combinations of conditions, we represent this in a decision table and test, then it will become too many. But we can consider pairwise testing, in which we have all possible combinations among two of the input present. So, we have all possible combinations of these two, these two, these two, these two, and so on, all possible combinations between any two if they are present, then it is called as a two-way testing. We similarly can have three-way testing. If we have all possible combinations of any three, let us say this, and this, and this, and so on, all possible combinations among the different parameters, then we have a three-way testing. Similarly, we can have a t-way testing. Now, let us understand the pairwise testing further. Let us, for simplicity, assume that there are two possible classes of input for pressure A and B, three possible input equivalence class input for temperature T1, T2, T3. For velocity, there are 6 velocity classes. Acceleration are 10, 20, 30, etc. Air density is some 1.1, 2.1, 3.1. Now, let us say we want to consider pairwise testing, and we need to have test case which will have any combination between two of these input present. Let us say, let us consider these two, pressure and temperature. So, our test case must have pressure A, temperature T1, pressure A, temperature T2, A T3, and B T1, B T2, T3. So, that is all possible combinations of pressure and temperature, and there are 6 entries here. Similarly, we might have let us say temperature and velocity. So, we will have 18 entries here. It is not necessary that they may be there on a different test case, but it may be that they are on the same test case. Some of these are present, let us say T1, when this is T1, this is, let us say, velocity is 1, velocity. When temperature is T2, velocity is 2, and so on. So, given the test case, set of test cases, we should be able to identify, given any two possible input values, any two parameters, we should be able to find all possible combinations of conditions. Any two may take temperature, air density, velocity, acceleration, or velocity, air density. In our set of test cases, we should be able to identify all possible combinations of conditions. This please remember that this is different from all possible combinations where we have 0 0 0 0 0 0 0 1 etcetera, all possible combinations of conditions, and that is too many. Here it is possible to drastically reduce the number of test cases. Now, let us see what is the reduction that is possible. If the number of input is 7 and each is a Boolean, then if we do a decision table based testing, then the number of rules or combinations of conditions is 2 to the power 7, is 128. But if we develop the pairwise tests, then we can do with 8. If the number of input is 13 and each can take 3 possible values, then the number of possible combinations or number of the columns on the decision table becomes 3 to the power 13, and this we can write 1.6 into 10 to the power 6, because this becomes 3 to the power 2 into 3 to the power 11, and that is becomes 9 into 3 to the power 11, and then we can find that it becomes okay. We can write here as 3 to the power 2 into 2 to the power 6 into 3. So, that is 3 to the power 12 into 3, and this is 9 to the power 6 into 3, and we can find that it becomes 1.6 into 10 to the power 6. It is 1.6 million test cases, but then if we do pairwise testing, it becomes just 15. Significant reduction can be achieved. Million test cases, it is very difficult to test. It will take years to run a million test case, but just see here we can test with almost as much effectiveness using only 15 test cases. Similarly, if the number of inputs is 40 and each one takes 3 only, 3 values, then the number of test cases is 1.2 into 10 to the power 19, and if there is a team testing these test cases in their lifetime, they cannot complete testing. But if we consider pairwise testing, then we can do with only 21 test cases, which is a manageable number. So, the point that trying to convey through this table is that the reduction in the number of test cases is significant, is dramatic in pairwise testing over a combinatorial test case design like decision table. Now, to gain further understanding into the T-way testing, two-way or pairwise testing, etc., let us look at some more concepts. A simple fault is called as a one-way fault. So, as long as a parameter has a certain value, this fault occurs. But if certain combination of two inputs Let us say when the temperature becomes 100, only when the temperature is 100 and also at the same time the pressure is 50, only in this situation the error occurs. If the pressure is 100 and temperature 60 and so on, the error may not occur. So, this is a two-way testing will detect this. A one-way testing of course cannot detect this, because we will have 100 as long as it reaches 100 and in some other test case it has reached 50, we would have a one-way testing. It is a important observation that in a majority of software, it is experimental empirical observation that in majority of software the fault consists of simple and pairwise faults. Several researchers have conducted experiments and have found that vast majority of the faults are either simple faults, where as long as that value is taken, that input value is taken, then it fails. Whereas, a pairwise fault, when two specific combination of input is taken, then the software fails. Let us see some example of a single mode bug. This kind of bugs are very common. Here, as long as this condition is satisfied, then the software fails. One specific condition is satisfied, the software fails. For example, as long as the duplex mode is chosen in a printer, irrespective of all other possible combinations, as long as it is a duplex option, then the printout gets smeared, irrespective of all other options, for example, printer type, color and so on. So, to test this, we just need to check that every option is taken by the test cases. The test cases give every option for all of the input. A double mode fault, here only if two specific combination of conditions are present, then the problem occurs. Just to give an example, the printout is smeared when the duplex is selected and the printer selected is 394. So, if you just select duplex and with some other model number, problem does not occur. If you use simplex with 394, problem does not occur, but only for this specific combination this occurs. So, this can be detected by pairwise testing, and in general we can have a n-way testing. We will just look at that in the next lecture, and we will look at an example of pairwise fault at the end of this lecture, and we will stop here, continue in the next lecture. Thank you.